We spent a lot of time in this class talking about functions, but we can also represent some mathematical ideas in sequences. Now, sequences are any set of numbers in a very specific order. Each element in the set is called a term, so we can call it the first term, second term, third term. We use an index, which is like a subscript, to identify which term we are talking about. So A sub 1, so A with a subscript of 1 means the first term. A with a subscript of 2 means the second term. So we're designating what part of the sequence or what part of the pattern we're talking about with the subscripts or the index. Now there are two general types of sequences, like overarching themes of sequences. You have your infinite sequences and your finite sequences. Infinite sequences have a domain which is the set of all positive integers, so we're not using negative numbers in sequences. It's just like 1, 2, 3, 4, 5. These sequences, since they're infinite, end with a ... to indicate that it's going to continue going on to infinity. Finite sequences, on the other hand, do not have a ... at the end because they are a set of numbers. So this sequence here in the example on number 2, this is a finite sequence with 5 terms. It doesn't have more beyond it. This is the whole sequence. So you have infinite sequences that go on for forever because of the ... and you have a finite sequence. Okay, so let's just kind of work with this notation a little bit. If we were to look at this first sequence, this first infinite sequence up here, we could label the numbers. So this is the first term, second term, third term, fourth term, fifth term, on and on and on until you get to what's called the nth term. Okay, the nth term is called your general formula, basically. It's a formula for any term in the sequence depending on what order it is. So we could answer a question like, let's say it said, what is A sub 2? So what is the second term in the sequence? That's easy, it's 4. If I asked you what the fourth term in the sequence is, you just count 4 numbers and that's the 16th. If I said, give me a formula for any term in the sequence, so the nth term in the sequence, you would just use the formula there. Okay, so that right there is essentially the formula or the pattern for the sequence when it has the n in it. Sequences can also be given to you in set notation. So if you look at B, it actually gives you the formula first. So 1 over k is my formula or pattern. And then it's saying use 1 over k, but make sure k is 1, 2, 3, on and on and on. So if I were to ask you to find the value of a sub 1, that means that the k value or the number in the sequence is 1. So we would do 1 over 1, which is 1. If I asked you maybe what a sub 3 is, okay, well, here's the first term, second term, third term. We're going to be plugging in that 3, the k, and we would end up with 1 over 3, which is 1 over 3. So any general equation, a sub k, is going to be 1 over k. That becomes the formula for this sequence. So in general, again, you have the first term, second term, all of the terms leading up to what's called the nth term. And if you have a formula with an n or a k, whatever letter you're using, generally it's n for these sorts of things, for the number, the spot that it's at, that's called the nth term, which is again kind of like our formula for these sequences. Again, finite sequences are kind of the same. You still have the first term, second term, third term, fourth term, and fifth term. You're just not going to have the ... or the nth term because you're only going to have the values between 1 and 5. So for example, you could still say a sub 1, well, that's 5, and a sub 3, well, that's 15. But if I gave you a sub n, if I asked you for the formula, we would have to figure out what the pattern is, which pretty obviously it's adding 5 each time or multiplying the set number it is by 5. But that number is only between 1 and n and 5. So these sequences, while they're very easy to use, have 2 different ways we can define them. The first way we're going to be defining sequences is called explicitly. Okay, there's another way called recursively. Explicitly literally looks like a formula. It looks like a regular formula where you would just plug in the term, kind of like a regular formula, where the terms are independent of each other. So you don't have to know all the terms in between to be able to figure out the next term in the sequence. And we're not going to do all of these examples for time's sake, but you guys can look at my notes, my handwritten copy of the notes to see B and C. We're just going to do A together. Example 1 says find the first 4 terms and the 100th term of the sequence. And we're going to write our answer in a sequence of numbers. So, okay, first 4 terms, that means I want A sub 1. Well, A sub 1 means plug in a 1 for n, literally just plug in the number. 1 squared minus 1, that's 0. A sub 2, that means I'm plugging in a 2. 2 squared minus 1, that's 3. A sub 3, plug in a 3. 3 squared minus 1, that's 9 minus 1. I just wrote cubed. 3 squared minus 1 is 8. And then the 4th term is 4 squared minus 1, which is 16 minus 1, that's 15. Now that's the first 4 terms of this sequence, and I'm going to pretend like I keep going, use that ... and find A sub 100, which means I'm literally just plugging in 100. So 100 squared minus 1 is 9,999. But we're going to write our answers as a sequence of numbers. So I'm going to use the squiggly brackets, and I'm going to just list out these numbers in the order that I got them so that they're in the first, second, third, and fourth order. I give myself a little break, ... to make it to the 100th. Give a comma with a ... since this is an infinite sequence, and close up the bracket. Okay, so you're just plugging in the numbers. Pretty simple to find the first 4 terms and the 100th term. Again, I do want you to try B and C, and I'm not showing you on the video, but you can pop over to the PDF of my handwriting notes to double check that you are correct. The second way that we can define or talk about a sequence is called recursively, or recursive formula. The word recursive, it kind of looks like it's going backwards, like it's reoccurring, which is exactly kind of what I want you to think about. A recursive formula gives you the first term and then a function for finding the subsequent terms based on that first term or based on the previous term. When you see the subscript of n minus 1, I want you to think of that as the previous term. That's all it means. Now, in a recursive formula, each term is dependent on the previous term, so you can't just plug in any general number. You actually have to build the entire sequence starting from sub 1. Okay, so if we look at example 2, it says give the first 6 terms, given a sub 0 is 1, a sub 1 is 1. Okay, so I'm just going to start with the first term. So a sub 1 is 1. They gave me that in the given. If I want to find a sub 2, I then have to switch to use this formula. And this formula says find the next one, so a sub 2, if you do a sub 2 minus 2, so that's 2 previous, and a sub k minus 1, which means the previous. What I mean is, if we want to find a sub 2, we're going to find a sub 2 minus 2, which is a sub 0, and a sub 2 minus 1, which is 1. Okay, well, they gave me both of those. A sub 0 is 1, and a sub 1 is 1, so a sub 2 is 2. If I was going to find a sub 3, again, because the formula now is bigger than 2, I'm going to have to use the formula part. A sub 3 minus 2, that's a sub 1. A sub 3 minus 1, just the previous, is 2, which means I'm going to be adding 1 plus 2. That's 3. We keep going because we're going to find the first 6 terms. A sub 4 would be adding a sub 2 and a sub 3, which is 2 plus 3, that's 5. A sub 5 would be a sub 3 plus a sub 4, the 2 previous and the previous, which is 3 plus 5, that'd be 8. And last but not least, a sub 6 is going to be a sub 4 plus a sub 5, which is 5 plus 8, that's 13. Again, the recursive formula just depends on the things that come before it. So k minus 1 or n minus 1 is the previous, k minus 2 or n minus 2 is 2 previous. But we're going to write this final answer as a sequence of numbers. which is started with, not 3, I almost wrote down a 3, 1, 2, 3, 5, 8, and 13. Those are the first 6 terms of this sequence. Okay, now most of them are not as complicated as example 2. Most recursive sequences only depend on the one right before it, like in example 3. It says find the first 4 terms and the 8th term, given that the first term is 3, and that the rest of them are found by taking the previous and adding 2. So the first term is 3, the rest of them are found by taking the previous term and adding 2. And this starts for all of the n's that are greater than 1. So, okay. If I was doing this first 4 terms, well, I already have the first one. Cha-ching! If I want to find the second one, I'm going to take the first term, I'm going to add 2, which means 3 plus 2 is 5. If I want to find the third one, I'm going to take the previous term and I'm going to add 2. 5 plus 2 is 7. If I want to find the fourth term, I'm going to take the previous term and I'm going to add 2. So 7 plus 2 is 9. There's the first 4 terms, but I also want the 8th. Now, I can't just say b of 8 because the formula for b of 8 depends on b of 7. So I actually have to find everything in between 4 and 8, and this is the downfall for recursive sequences because it's not like an explicit where I can just plug everything in and just go. I actually have to do all of this math to find all of the pieces right in between it. So we do all of the terms of this sequence leading up to the 8th so that I know that the 8th term is 17. To write this as a sequence of numbers, it would be 3, 5, 7, 9, 11, oh, not 11. We just wanted the first 4, sorry. Dot, 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 17, and continuing on. The first 4 terms and the 8th term. Okay, number 4 I'm going to leave for you to check with my notes. So go ahead and try number 4 and then check it against my handwritten notes, please. Another thing we can do with sequences is we can talk about their limits. Now, we've done limits before, especially when we did polynomial and rational functions. We talked about the limits of those functions. Well, sequences can also have limits, but we're going to use vocabulary that says that the sequence converges or diverges. If it converges, then the limit of the sequence is the number that it converges to, and diverges just means that the limit is infinity or it doesn't come together. But the way we're going to do this, we're going to bring back Bobo and eats DC for the converging sequences, and any Botten sequence, bigger on top, which has no sequence, it's diverging. Okay, so we just need to be able to tell if the formula of the sequence is a Bobo, Botten, or eats DC, and we should be able to answer these questions. So we have this infinite sequence here, and this first infinite sequence, it straight up tells me what the formula is. I don't have to do any work to determine what the sequence formula or pattern is. Now, this pattern, this f of n, is 1 over n, and that's bigger on bottom. The exponent is bigger on bottom, which means it's going to converge because it has a limit, and the limit as n, not x, we're using n approaches infinity of that sequence, 1 over n, is 0. Where did I get the 0 from, you ask? Right here. Bobo is always going to be 0. So a couple things changed with the limit. Number 1, we're not using x's, so make sure that you have n approaching infinity. And yes, you could write f of n right here, but since it's a sequence and not truly a function, we're going to be putting the sequence formula here, or the pattern of the sequence for my limit statement. Now if we look at b is kind of interesting because it doesn't automatically tell you what the formula or the sequence pattern is. So we have to figure it out. Here's what we do when we need to figure it out. First of all, list the order of the sequences above it. And then look for a pattern comparing the numbers in the sequence, the term numbers, with the actual numbers in the sequence. So if I look at this, to go from number 1 to have 2 over 1, it's like we add 1 to the number and then just use the regular term number. Now let's make sure that that fits everywhere else. For the second spot, 2 plus 1 is 3, and then 2 and that works. 3 plus 1, 3 and that works. 4 plus 1, 4 in the denominator. Hey, that's my pattern right there. So if that's the pattern for this sequence, this is an Eats DC. The exponents are the same, so we're going to divide the coefficients. The coefficients are both 1. So this is going to converge, because Eats DC is a converge. And it's going to converge to the limit as n approaches infinity of this function that we just wrote, n plus 1 over n, equal to 1. Letter C, again, it doesn't give me the formula title, so I'm going to have to figure it out. So here's all the term numbers. And this one's pretty simple. Do you notice the pattern here? Yeah, we're just multiplying by 2. So the function we have is just multiplying 2 times the term number. But I'm going to write this as 2n over 1. Because that's going to help me realize that this is a bigger on top function. So this one is going to diverge. And while diverge answers the question for the sequences, we're just going to go a step further and talk about the limit since we already understand these limits. The limit of, as n approaches infinity, of this sequence, 2 times n, is going to be infinity. It's going to keep going. So it doesn't converge to a certain number, so we just answered diverge, but we know that it's because the limit goes to infinity. Now this last one is very interesting. Some things you might want to notice. First of all, ooh, yay, they gave me the formula, but that this is also kind of weird. Notice that we're going from -1 to 1 to -1 to 1, and then keep going with negative 1s, right? So this is what's called an oscillating sequence. And this is different than the other ones because if you notice it's oscillating back and forth between two numbers, here's what it might look like on a graph. Here's -1 and 1. So we have the first term. So at 1, the term is -1. At 2, 1, at 3, -1, at 4, 1, on and on and on. If we were to graph this looks a little something like that, where it's going to continue on doing this over and over, oscillating between these two numbers. And since it's oscillating at the very end towards both of the infinities, it's not actually getting towards any particular number because it would just turn right back around again. So this limit does not exist. So this is a neither converging or diverging sequence because it's oscillating. It's not getting close to any particular number, be that an actual number like 1 or 3 or an infinity. Finishing out these sequences, sometimes our sequences are not given to us in a sequence pattern. They're given to us in the formula for the sequence. This is an explicit formula here, which is honestly more helpful because we really just need to decide if this is Bobo, Botner, Eats, DC. So these exponents for my n values are the same. Exponents are the same. So we're going to divide those coefficients. We know that this converges. It's a converging sequence because it's Eats, DC. And the limit as n approaches infinity of this sequence, 3n over n plus 1, is going to be when I divide those coefficients. So it's 3 divided by 1, which is 3. Again, that was E. F over here, we just already have the pattern, which is ideal because now I can just decide if this is Bobo, Botner, Eats, DC, but obviously this is bigger on top, which means this is going to be a diverging sequence. It diverges. And just because it's good practice, we can still write the limit statement the limit as n approaches infinity of n cubed plus 2 over n squared plus n is going to be infinity. But we don't include that as like technically part of this answer because it's just asking if it diverges. And last but not least, letter G here. We look for the highest exponents. Those highest exponents are bigger on bottom. This is a Bobo. Bobo is a converging sequence, so we know it converges. And the limit as n approaches infinity for this entire function, entire sequence, sorry, is going to be 0. Where'd I get the 0 from? From Bobo. Bobo tells me that the limit is 0. That's what it's converging on, or getting closer and closer to. These are probably the most important formulas for you today to have, so we're going to put some clouds around these. We have two types of sequences, two patterns of sequences. The first one is called an arithmetic sequence. It looks like arithmetic, but it's pronounced arithmetic. These are sequences that add or subtract terms. They have what's called a common difference, or how much we're adding and subtracting every time. But these two formulas, these are the formulas for this particular type of sequences, explicit and recursive formula. This is 100% the most helpful thing to have on your notes for today. Okay, we're going to be utilizing both the explicit formula and the recursive formulas for these arithmetic sequences. Now, the explicit formula says any number in this sequence can be found by starting with the first term and adding one less than the term number times that common difference. A recursive formula has two parts. We have to give the first term, so you have to tell me what the first term is. And then you say any term after that is found by taking the previous term and adding that common difference for any n greater than or equal to 2. That part is always just like tacked on at the end. So let's check out example 6. It says, for each of the following, find the common difference, the 10th term, and a recursive formula for the nth term, an explicit rule for the nth term. All right, let's do this piece by piece. First things first, it says find the common difference. And guys, don't overthink the common difference. Here's all we're doing. How do you go from 6 to negative 2? You add 4. How do you go from negative 2 to 2? Oh, check it out. We have a pattern in the sequence. That means my common difference, answer to A, the common difference is a positive 4. Don't overthink that part. It's just the pattern, essentially. The common difference is just what is it moving by? What's it going up or down by? Okay, if we find the 10th term, that means we're looking for A sub 10. Now, we have a formula, an explicit formula for this, where we need to do A sub 1 plus n minus 1 times d. Okay, I can do that. A sub 10, the first term in the sequence, well, that's negative 6, easy. And then 1 less than the term we're on. Well, we're on term 10, so 1 less than 10 is 9. And then we already know our d value, which is 4. So just like plug that into a calculator. Negative 6 times 9, or plus 9 times 4 is negative 6 plus 36, which is 30. So A sub 10 is 30. That would be the 10th term in the sequence. I didn't have to find all the terms leading up to it because we used the explicit formula. But let's write that recursive formula. Now that we know the first one, we knew the first term was negative 6. We know any term after that is going to take the previous term and add 4, given that n is greater than or equal to 2. Again, I just filled in that formula that we put a little cloud over at the top of your notes. And the explicit formula, again, if I have a sub n, it's going to be the first term, a sub 1, negative 6, plus n minus 1 times d, which we found to be 4. Now, leaving it like that's kind of ugly, and if we make it a little bit more useful for ourselves, we're actually going to distribute that 4 and then combine like terms so that we have a formula that's essentially in what you would look like slope-intercept form, but it's not because it's a sequence. But you do have essentially a slope, I'm using air quotes because that's the common difference, and you have the 0 term, which is the, y-intercept, if you will. Okay, so again, just walking through that because I went a little fast. D is the common difference. How's the pattern changing? The 10th term, you just fill in the explicit formula with what you know. We know the first term. We know that we're on term 10, so 10 minus 1 is 9. And we know the common difference is 4. Bing, bang, boom, we have our 10th term. The recursive formula starts with the first term. You just have to tell me what the first term is, which, boom, we got it. And then fill in the rest. A sub n equal to the previous term plus the common difference, which was 4. And then tack on the given n is greater than or equal to 2. And for the explicit formula, we fill in the explicit formula with what we know. We know the first term is -6 and the common difference is 4. And then we just clean it up by distributing and combining like terms. I'm going to leave letter B for you to do on your own. If you want to check your work, again, just check the PDF of my handwriting so that you can make sure you're doing it right. Let's move on to geometric sequences. So geometric sequences are a different type of sequence. They're pretty common, but geometric sequences are sequences whose successive terms have what's called a common ratio. That means that these are not changing with addition and subtraction, but by multiplication and division, or multiplication by fractions. So multiplication by whole numbers or multiplication by fractions. And it still has a different explicit and recursive formula, but they're actually easier to use, in my opinion. Geometric sequences, the explicit formula for any number in the sequence is taking the first term and multiplying it by the common ratio raised to the n minus 1 power. The recursive formula, again, starts with the first term, but then any term after that is just the previous term, literally just times the common ratio for any n greater than or equal to 2. So we're going to do the same thing that we did in example 6 with example 7. We're going to find the common ratio, this time the 8th term in the sequence, a recursive rule, and an explicit rule. So if I want to find that common ratio, all I need to do is figure out how these are changing. Using multiplication or division, since I know this is geometric, how do you go from 3 to 6, and 6 to 12, and 12 to 24? That pattern should be the same every time. That's how you know it's geometric. Okay, great. So we know that the common ratio is 2. Check, done, that's awesome. If we want to find the 8th term in the sequence, so we're looking for a sub 8, we're just going to fill in the explicit formula for what we know. Well, we know that the first term is 3, so a1 is 3. We know the common ratio is 2, and since we're looking for 8, we're going to the 8 minus 1 power, which is 7. So we can throw that into our brain or in our calculator, and we'd get that the 8th term in the sequence is 384. To write the recursive rule, 2 parts, it starts with the first term, and we can just look at the sequence to see that the first term is 3. And any term after that, you take the previous term and you multiply it by 3. And that's fine to write it like that, but I actually like rearranging this to have the 3 go in front. Sorry, not 3, 2, because our common ratio is 2, I apologize. So 2 times a to the n minus 1, given n is greater than or equal to 2. So I just like putting the common ratio first, because then it actually looks like just a multiplication problem where we could plug in the term after it. And last but not least, the explicit formula. The explicit formula says to take the first term, multiply it by the common ratio, and raise it to the n minus 1 power. Now, unlike arithmetic sequences, we don't have to do any sort of distribution and rearranging. The geometric sequences are perfect the way that you just fill in the common ratio and the first term. Okay, B is for you to do and check with my PDF notes as we have done the rest of this lesson. All right, so these constructing sequences examples are really pretty interesting. We're just going to do example 8 with the video and example 9 and 10 because they're easier. You will do just with my handwritten notes checking your work for time's sake. Now, number 8, it says the second and fifth terms of a sequence are 3 and 4 respectively. I'm going to stop reading right now and just write down what that means. That means that a sub 2 is equal to 3 and a sub 5 is equal to 24. Okay, so the second and fifth terms are 3 and 24 respectively. Okay, great. Find the explicit and recursive formulas for both if the sequence is arithmetic and geometric. So we're going to do this twice. This side of my paper is going to be for the arithmetic, and this side is going to be geometric. Okay, great. So what we're going to do first, we're going to take the arithmetic first. Okay, we still have that information up there. And what we're going to do is we're going to write down both of the terms in their explicit version. So what I mean by that is an explicit arithmetic equation is, or sequence is a sub n equal to a1 plus n minus 1 times d. Okay, I'm going to start with the bigger number first. So we know that 24, that's the term, is equal to a sub 1, I don't know what that is yet, plus n minus 1. Now 24 was with term number 5, so 5 minus 1 is 4 times d, and I don't know d yet. Okay, if we write the second one, we have 3, that's the term, is equal to a sub 1, which I still don't know, plus n minus 1. So 2 minus 1 is 1d. Okay, this is what we're calling the setup step. We're setting up literally a system of equations. It's as if this is x and y, and we need to solve for x and y. So we're going to solve by elimination. So what we do here is we actually subtract. And that's why I started with the larger one. So I'm going to subtract this entire bottom equation. 24 minus 3, that's 21. a1 minus a1 goes away. 4 minus 1 is 3d. Oh, check it out. I only have one variable left. I can solve for d. d would be equal to 7. So we found the common difference. Yay! I just need to find the first term. So that's our next goal. Find a sub 1. Okay, well, let's take back the very first equation we have, 24 equal to a sub 1 plus 4 times d, but we now know d is 7. So we have 24 equal to a sub 1 plus 28, or that a sub 1 is equal to negative 4. These two pieces, the a sub 1 and the d, are all that I need to write both forms of this equation. Okay, so if I wrote the explicit, remember the explicit is a sub n equal to a sub 1 plus n minus 1 times d. That's the formula. So then we can just clean this up by distributing and rearranging it for a nice, pretty looking explicit formula. For the recursive formula, we need two parts. We just need to list out the first term, and then we need to say that any term after that is just taking the previous term and subtracting 4, given that n is greater than or equal to 2. So, whoa, what happened? You're right. So we set up a system of equations utilizing the formula version of the information. We were told that the fifth term, it says 4 because it's n minus 1, so 5 minus 1 is 24. We were told that the second term, 2 minus 1 is 1, is 3. This allows us to set up a system of equations and solve by elimination. 24 minus 3 is 21. a1 minus a1 crosses out. 4d minus 1d is 3d. Solve for d. Then we use this value in either one of the two equations. I always use the top one. That's just my habit. I rewrote the top equation, but instead of writing d, I wrote 7, because then I'm able to solve for a1. And once I have the common difference and the first term, I can fill out both the explicit formula and rearrange it, and the recursive formulas. Let's do the same thing, but this time for the geometric version of this sequence. So geometrically, the explicit formula for a geometric sequence is a sub n equal to a sub 1 r to the n minus 1. So let's again set up our information we were given in that form. We were told that the fifth term is 24, We don't know what a sub 1 is. We don't know what r is, but we do know that was the fifth term, so 5 minus 1 is 4. We were also told that the second term is 3. Don't know the first term, we don't know the r, but we do know that 2 minus 1 is 1. That's our setup step. For geometric sequences, you are not subtracting this system of equations. You're going to do something weird, and you're going to divide them. What? Yeah, we're going to go ahead and divide. Okay, so 20, just divide the top divided by the bottom. This is weird. 24 divided by 3 is 8. A1 divided by A1 cancels out. R to the fourth divided by R to the first power is R to the 4 minus 1, or R cubed. If we take the cube root of both sides, we get that r is equal to 2. That's great. I needed that common ratio. So I divided these, and then I finished solving for r. And once I know r, I can plug that r back into one of the two original equations. Doesn't really matter which one. I always do the top one because that's what my habit is. 24 equal to a sub 1 times r to the fourth power, but r is 2. 2 to the fourth power, and 24 divided by 2 to the fourth power, actually, is going to end up being 3 over 2. (24) divided by 2 over 4, or 2 to the fourth, which is 16. Okay, great. So now I have the first term, and I have my common ratio. I can start plugging in everything else. Sorry, I didn't write down what we did here. Find a sub 1. If I start with the explicit formula, again, looking at the formula that it was given to me, the formula says a sub n is equal to the first term times the common ratio to the n minus 1 power. And if we're doing the recursive, we have a sub 1 equal to 3 over 2. That's the first term. And any term after that is going to be 2 times that common ratio times the previous term, given that n is greater than or equal to 2. Again, I just rearranged them. I put the common ratio first as opposed to second, even though the formula says second. Doesn't matter. So I know that these problems are a little bit wild. But all you have to do is remember to set up the information you're given in the formula version. Okay, this is the formula. The fifth term is 24. We don't know A1, we don't know R, but 5 minus 1, since it's the fifth term, is 4. Set up both of them that way, and for geometric, you're going to divide. Arithmetic, we subtracted. For geometric, we divide. We'll be able to solve for our common ratio, which then allows us to solve for the first term, which then is all the information we need to plug it into both the explicit and the recursive formulas. Now, like I said earlier, we're not going to do example 9 and 10 together. They're easier because you're only doing either a geometric or an arithmetic sequence. You're not doing both in one problem. So take your time and go through that, and you can check the PDF of my handwriting for you to be able to do those. Have a nice day, everyone.